Thank you, Terry. I first want to thank the management committee of this cost action for inviting me to give this talk. I will present you some ideas that are quite a bit different from the preceding one, from the presentation from Roy. And mainly, I will speak about the habitability from the life point of view and not from the planetary point of view. So this is the title of the conference, and my view is about the origin of life, the transition from non-life to life. So it is generally considered that a condition for the origin of life is the presence of organic matter. The second one is the presence of liquid water, and lastly, the presence of energy. But this is in some way quite loose, and I would add a comment about the presence of organic matter. If organic matter is life, it reminds me the vitalist view that life comes from organic matter, and I would prefer something more strong to explain why organic matter is needed. And about energy, yes, we need energy, but which kind of energy? So I will try to answer this question and through what may be a scientific approach. And for this, I will start from the ideas of adipose, and especially the idea of dynamic kinetic stability, which is spoke about yesterday, and which is a kind of stability that is specific to processes of reproduction, namely replication or autocatalysis. So, yesterday, Adis explained that there are two kinds of stability related to two kinds of mathematical logic. Thermodynamic stability is related to the second law of thermodynamics and corresponds, in fact, to the molecular interpretation of entropy through statistical mechanisms, corresponding to the theory of Boltzmann. And the second kind of stability is related to Malthus' theory, the power of reproduction and exponential growth, and it is, in fact, the ideas of Malthus that more or less induced the Darwinian theory of evolution. So the point is that under certain conditions, the description, the stability of Malthus can be more powerful than that of Boltzmann. And just a point about stability. Stability, when we speak about stability, we think also of the possibility of changing something. So it means that we start from a less stable state to have a more stable state. And this is connected to the concept of stability. But if we think to the reverse transformation, it means that the reverse transformation is unlikely to take place, or at least, or impossible. And in fact, this means that the concept of stability is connected to the concept of irreversibility. And if we have two kinds of stability, we must have two kinds of irreversibility. So the thermodynamic irreversibility is connected. So I show an analogy to explain what is thermodynamic irreversibility. We start from an egg, we break the egg, then we mix. Of course, there is no change between this state and this one. However, if we try to unfold the story in the reverse direction, everybody knows that this is not possible. The only thing that we can do is annihilate. If we look at dynamic kinetic stability, the other form of stability, we start from the egg, we get a chicken, and of course you can get another egg, and you have a cycle, a reproduction cycle. Of course, the story can't unfold in the reverse direction. And in fact, the important point here is that you get several eggs from a cycle which explain the exponential growth. So, in fact, the irreversibility in these systems is related to the fact that the system, the cycle, is open, and so that we can receive energy from the environment. And this is closely connected to the description of the paradox of life by Schrödinger. We explained that the decrease in entropy across, which is connected with the development of living organisms, is in relation to the fact that these systems are open and they must receive low entropy energy from the environment. And this low entropy energy is converted into heat or inactivated products which generate a huge amount of entropy in the environment so that the local decrease is compensated. And in this way, the violation of the second law can be avoided. So this means, in fact, that the development of living organisms requires far from equilibrium conditions. So if we look now at the origin of life, it can be described as a change in state starting from an inorganized state and reaching a system that meets a definition of life. And in fact, this is a difference. We start from a probable, highly probable state. We go to an improbable organized state. But it has been all explained here that this transition like this one is unlikely to take place. And in fact, it is so much improbable that it constitutes a violation of the second law of thermodynamics. If we try to make this transition by a gradual process involving several intermediate stages, the problem here is that the probability of the final state will not be changed by making the transition in several stages. So we do not solve the problem by making the transition gradually instead of in a single transition. So the only possibility is to stabilize the intermediate stage. And in this way, we have a lifetime so that we can have new improbable transition leading finally to a system meeting a definition of life. But of course, here the question is there a mean of increasing time stability without changing thermodynamic stability? And the possibility is to use systems that can replicate themselves so that we change the stability, the time stability from one system to several generations of a system and, of course, a numerous offspring. And in this case, there is a possibility of a drift towards increased dynamic kinetic stability. And in fact, evolution can take place toward less probable but more persistent states. And this is possible for entities capable of multiplying themselves. So I took this scheme from the talk by Adipros yesterday. So this means that using this description of the origin of life, we have only a single evolutionary process that encompasses a chemical and biological phase. And we can start from simple replicating system. And this means that the origin of life is neither the egg, neither the chicken, but it can be much simpler systems that are able of reproducing themselves, such as autocatalytic system, in which the product catalyst is a catalyst for its own production, temperature replication, such as a replication of nucleic acid, or vesicle division. So, an important point is that all the replicating systems correspond to cycles of replication. And the question is, as I mentioned, the importance of irreversibility is how to make a chemical cycle, cyclic chemical process irreversible. So we start from a reactant, a catalyst, we get an intermediate, and a metabolite. This is, in fact, the simpler cyclic system, a catalytic cycle. So the question is to make it irreversible. The question is to make the reverse reaction slow enough to avoid the reverse process. And this can be made by introducing energy. And in fact, it is possible if this kinetic barrier is high enough so that the reaction is slow at the time scale at which the overall cycle proceeds. So this means that part of the energy that is introduced in the system has simply to be spent to avoid the reverse reaction. It means that irreversibility has an energy cost. It is the cost of kinetic irreversibility. And I will make a connection with an observation that was made by Albert Eschenmoser, that the development of a metabolism requires species to be held far from equilibrium by kinetic barriers. I will make the analogy with the conversion of the potential of energy of water into electricity. Of course, we need a device, an alternator, and things like that, but we need also a dam. And if we consider the metabolism that can emerge from activated species leading to inactivated products through metabolites, for this system to work, we have to avoid side reaction leading to side products or leading directly to products. And this can be made by kinetic barriers. And these kinetic barriers, we can analyze them quantitatively by considering that any reaction, for example, the reaction of this metabolite, metabolite I, that into side product I, through the transition state. The rate constant of the reaction will be related to the absolute temperature and the kinetic barrier. The other parameters are, in fact, physical constants. So this means that we can have a relationship between the temperature of the system, the lifetime of the system, expressed by the kinetic rate constant of the half-life, and kinetic barrier. And we have a relationship between these three parameters that can be analyzed using this graphical representation. Here you have the kinetic barrier, here the half-life of the system on a logarithmic scale, and here you have a linear variation with a slope that only depends on temperature. So if we select a temperature of about 300 Kelvin, this is a warm temperature, warmer than on icy worlds. It's close to the temperature of the Mediterranean Sea in summer. So if we select a range of half-life from 1 second to 100 years, covering the lifetime of many living organisms, this corresponds to a kinetic barrier of 75 to 125 kilojoules per mole, which is reasonably close to an order of magnitude of 100 kilojoules per mole. And what is important about this value, it corresponds to a significant fraction of the free energy of the covalent bond. And this is important because this means that covalent bonds are particularly fitted for the emergence of life. So if we now look at the need for energy for sustaining the origin of life, so with this diagram in which you have energy of different, with different units, kilojoule per mole, the frequency of electromagnetic radiation or the corresponding wavelengths, with here the infrared, visible, and UV domain. We can put on the same diagram this green rectangle corresponding to the free energy of activated biochemical intermediates such as ATP, and we can add the cost of irreversibility, and we get the free energy requirement for the origin of life. So it corresponds more or less to the visible and UV domain of electromagnetic radiation. If now we look at thermal energy, this can be analyzed using the black body radiation. And here you have the curve for a star at a temperature of 6,000 Kelvin, a colder star with a temperature of 3,500 Kelvin, the temperature of the magma of the earliest, and here the critical temperature of water, which is representative of hydrothermal system, and that doesn't fit this condition, this requirement. Here you have the lightning, process like lightning that fit the requirement for the origin of life. The important point is that present-day life is capable of harvesting, of having energy for more diluted energy sources, such as transmembrane gradient. But it must be considered that this is the consequence of the existence of a very complex system, which is in fact ATPase, which is a molecular machine with in blue here a part which is in fact a rotor and which rotates and then synthesizes ATP from protons translocating across the membrane. And in fact, it can be considered as an energy concentrating machine. And it is made of about 3,000 amino acid residues. So it is highly unlikely that life started from this kind of processes. So I would make an analogy with convection that takes place when liquid layers are heated by the bottom, and in which we observe convection. But this occurs only if the temperature of the bottom exceeds the temperature of the top with a threshold in that temperature. Having a temperature of the bottom over the temperature of the top is not enough, in fact. And this means that a critical potential threshold is required for the emergence of dissipative structure. And it is likely that it is the same for life. And we can consider that a similar threshold is needed for the emergence of life, and that threshold may be associated with what I call the cost of irreversibility. So this was the title of my talk. Being thermodynamically favorable is not enough for the origin of life. And so that I come back to my first slide, we can speak about the ability in the universe in relation with the origin of life. The first observation, it is that habitability for life is different from habitability for the origin of life, which is in fact much more stringent. About the presence of organic matter. In fact, this presence of organic matter for for starting life is in fact correlated with the stability of covalent bond, which is in fact a consequence of the temperature in which water is liquid. About what I said about the temperature of about 300 Kelvin. So the last point is about the presence of energy. We need a free energy potential equivalent to that of life. So the best condition for the origin of life would lie in the surface of planets or moons receiving light from stars or prone to storms in which we have lightning and processes like this one. So I want to thank my coworkers, the collaboration that we have, and especially the work that has been, the exchanges that we had with Professor Adipros, who is in this audience, and which was of great help in the development of these ideas and the organization that funded our research. Thank you for your attention.